歡迎各位嘉賓出席由 CAiRS 主辦嘅網上研討會，而家正式開始。為咗確保研討會順利進行，請各位將麥克風設定做靜音。今日嘅主題係產品可靠及系統安全，業界面對嘅挑戰同埋機遇。我係今日研討會嘅司儀 CAiRS 嘅 Assistant Technical Marketing Manager Samuel 房。隨住市場嘅發展，產品亦都變得更加多元化、智能化、電子化，網絡產品亦都日益增多，所以我哋更加會關注產品嘅可靠同埋系統嘅安全。咁究竟產品可靠同埋系統安全會為業界帶嚟啲乜嘢挑戰又或者機遇呢？今日我哋好榮幸請到各位嘅專家同埋業界嘅名人同大家一齊分享一下。好，首先我介紹幾位嘉賓先。喺我嘅右手邊係CAiRS 研發中心總監同埋執行董事容錦全教授。好多謝容教授。第二位喺容教授隔離嘅係金山工業集團有限公司執行副總裁李耀祥博士。大家好。好多謝Dr. Bani。Okay, the first speaker is Dr. Steve Bose, Associate Professor, the Hong Kong Polytechnic University. Thank you, Dr. Bose. 好，歡迎幾位嘉賓。再一次多謝幾位百忙之中抽空我哋嚟到我哋嘅研討會。Thank you for all the guest speakers to take your time to our webinar. 好，而家研討會正式開始。咁如果各位對研討會嘅內容有咩問題，可以隨時喺畫面上面嘅 QR code 掃描，輸入你嘅問題。喺答問環節，我哋會隨機抽出問題要作出解答嘅。好，事不宜遲啦。首先，我哋由 CAiRS 嘅研發中心總監同埋執行董事容教授為大家揭開呢個研討會嘅序幕。容教授會為我哋介紹 CAiRS 產品及可靠性、系統安全上面嘅研究嘅。有請容教授。
大家好啊，歡迎大家參加呢個網上嘅研討會。咁我作為第一個講者咧，我好希望咧就將我哋呢個研發中心點解成立喺香港，同埋我哋研發中心係究竟做乜嘢嘅，先嚟做一個簡單嘅介紹啊，用20分鐘到介紹一下。咁我哋嘅研發中心全名咧就係產品嘅可靠性暨系統嘅安全一個研發中心。英文咧係 Center for Advances in Reliability and Safety。咁呢研發中心咧係由理工大學去 initiate 嘅，咁亦都得到業界廣泛嘅支持。特別咧當中有2個嘅商會係好支持我哋嘅。第一個就係香港電子業商會啦，另外一個咧就係香港電子總會。我希望用幾個嘅 W 嚟介紹一下我哋嘅 centre。第一個咧就係 What， 咁究竟我哋 centre 係搞乜嘢嘅咧？我哋盼望咧，我哋有一個 vision 嘅，其實咧我哋盼望能夠成為區域性嘅，甚至世界性一個 leading hub， 係特別喺 reliability and safety 嘅 innovation 作研究。大家都知道，無論產品或者係零部件或者甚至系統咧 ，reliability and safety 咧好重要嚇。咁咧喺今日咧普遍嘅研究嘅當中咧，呢方面着重呢2方面研究比較少嘅。我哋盼望咧能夠咧利用人工智能啦，同埋工業界嘅大數據嚟成為我哋一個幫助。再加上一啲 reliability and safety 嘅 model 咧，去將我哋嘅產品同埋系統嘅可靠性同埋安全性提高嘅。我哋嘅研發咧，應該係放之四海皆準。換句説話咧，喺好多個行業咧，我哋都可以應用嘅。譬如話電子業啦，譬如話生產零部件嘅啦，譬如話 public utilities 啦，或者係 transportation 啦。一陣間我都會有一啲嘅例子同埋一啲嘅合作夥伴咧介紹俾大家。希望咧藉住呢啲嘅研發咧，我哋對於香港成為一個智慧城市咧都有所貢獻。咁最後我哋一個 vision 就係盼望所有喺香港，無論係設計嘅、製造嘅，或者係 commission 嘅，無論係產品或者零部件或者系統，都能夠 有非常高嘅 reliability 同埋 quality 同埋 safety。咁呢個咧某個程度上就係一個 branding 啦。好啦，講到可靠性同埋安全性，其實我諗呢個重點喺咁多年嚇，自從有產品有 system 開始嚟講，大家都着重啦。咁點解仲需要我哋存在咧 ？Why？ 嗱，雖然即係大家都好着重產品同埋系統嘅可靠性同安全性，但係直至今日，我哋仍然咧係有好多個系統同埋產品咧係遇到 reliability 同埋 safety 嘅 problems。咁嘅原因喺邊度咧？個原因就係我哋而家好多嘅系統同埋產品咧，基本上咧都係一啲好 complex 嘅 system， 裏邊包括咗電子零件，亦都包括咗啲機械嘅零部件。呢啲嘅電子零件或者機械零部件咧，都會有佢嘅 aging， 佢 aging pattern 都唔同。再加上我哋仲有 software， 而啲 software 咧，我哋都會有陣時候見到有啲 latent 嘅 software faults。所以因為咁嘅原因咧，再加上我哋喺用呢啲產品同埋系統嘅時候咧，我哋其實有好多變數嘅。呢個變數咧嚟自用家或者用者 user 嘅一啲嘅變數啦 ，user conditions 咧，亦都有一啲嘅環境嘅變數，無論佢哋系統嘅運作嘅時候嘅溫度、濕度啊等等咧，會造成一啲 unpredictable 嘅 failure。咁我哋研發中心採取嘅 approach 係乜嘢咧？用一個簡單嘅例子嚟去解釋一下，就好似咧喺一個系統或者產品裏邊咧擺咗一個醫生。呢啲系統同產品咧好多唔同嘅零部件。呢個醫生咧就探索唔同嘅零部件咧，佢哋嘅一啲嘅健康指數。譬如等於一個人體，當然我哋發燒係唔想啦。你可以當發燒一個 anomaly 或者一個 failure， 但係發燒之前，其實喺我哋嘅身體好多嘅健康指數咧，佢係有緊變化，甚至有啲 data trends 嘅。如果你能夠喺一個系統同埋產品，佢哋嘅關鍵性嘅零部件或者某啲嘅地方擺上適當嘅一啲嘅 sensor， 量度佢哋啲健康指數，透過大數據嘅分析，我哋就可以咧能夠話到俾大家聽，呢個系統同產品佢嘅 reliability 同 safety 嘅 level 有幾多？咁總嘅嚟講咧，喺第二點嘅 bullet point 咧講得好清楚啦。我哋希望咧係利用 reliability physics， 再加上一個實時嘅去檢測呢個系統同產品嘅一啲嘅 data， 一啲嘅指數 index， 再加上大數據同埋人工智能嘅 modeling 嘅分析，能夠咧喺第三個 bullet point 俾我哋睇到呢個系統同埋產品實時嘅健康情況，甚至咧我哋可以為呢個產品同埋系統講出佢剩低嘅有效嘅生命週期係幾多，而呢個嘅指數咧係可以不斷嘅 update。我哋總嘅嚟講咧有幾個大嘅範疇嘅 research objectives 嘅。咁啊，首先我哋要睇睇而家我哋搞 reliability and safety 究竟有啲咩 research gaps 啊？咁我哋亦都會利用唔同嘅人工智能嘅 technologies 啦、methodologies 啦，去套用喺產品同埋系統嘅可靠性同埋安全性上高。總嘅嚟講咧，我哋會用兩大範疇嘅研究方案或者 approach， 一個咧就叫 DDM（Data Driven Methodology）， 另一個咧就係 POF（Physics of Failure）。兩者咧缺一不可。我哋將呢個兩大研究範疇咧係 integrated together， 糅合咗在一起。咁我哋盼望咧能夠最終做到一個 predictive 嘅 failure， 唔係 preventive， 當然更加唔係 corrective， 係 predictive 嘅 failure 又好 anomaly 又好，從而咧俾大家能夠對自己嘅產品同埋系統咧有一個比較清晰嘅一個印象，知道我哋嘅可靠性同埋安全性去到邊度。咁究竟我哋嘅center 我哋嘅研究係點樣運作嘅咧？我哋主要咧將我哋嘅研究咧係化做5大範疇。每一個範疇咧畫面上面已經講得好清楚啦，我就唔會去詳細讀出嚟。呢5個範疇咧係互相有聯繫嘅。咁呢5個範疇下低咧都有唔同嘅 projects。咁總共咧暫時嚟講咧，我哋會有15個 projects。當然唔排除咧 喺同一啲業界再繼續去研究、開發同埋討論嘅時候咧，我哋會有第16個、第17個嘅 project。我哋盼望咧，唔單止我哋係有呢15個 project， 呢15個 project 只不過係一個起頭。盼望業界咧俾我哋有更多嘅資訊，從而咧我哋能夠成立一啲研究方案，成為第16、17、18一路落去。咁究竟我哋研發嘅團隊係邊一紮人咧？咁頭先講過啦，就係香港理工大學initiate 嘅啦。咁我哋有2大嘅合作伙伴啦，都係我哋 supporting organizations。咁就係香港 EIA 同埋香港 EIC。咁我哋都有個別嘅 supporting 嘅 companies 啦，一啲係搞緊尖端科技microelectronics 嘅，例如即係 Compass 啦、ASM 啦，亦都有啲嘅transportation 嘅公司啦，香港小輪有限公司啦。除咗一啲之外咧，其實我哋都有好多唔同範疇嘅 collaborators。我哋嘅 technical support 係 NVIDIA， 係一個非常出名嘅生產先進電腦配件同埋 supercomputer 嘅間公司啦。我哋嘅合作伙伴咧嚟自幾個範疇，譬如第一個係講緊我哋嘅 transportation 啦，有 HKEIC 啦，有 CAiRS 啦 ，CAiRS 主要係負責研究啲鐵路嗰啲嘅路軌嘅情形啦。咁亦都有頭先講過香港小輪有限公司。咁第二個範疇咧就 public utilities。我哋有全香港2大嘅 public utilities 啦，一個就係中電啦 CLP 啦，另一個咧就香港熱力直港燈。咁工業界咧亦都好多個朋友咧同我哋合作嘅。咁唔盡錄啦嚇。呢啲嘅合作嘅伙伴咧都已經同我哋簽晒好多嘅合作嘅條款，包括咗 NDA。咁換句説話咧，我哋都係未來嘅日子咧好着實嘅，同佢哋去解決一啲 reliability 同埋 safety 嘅 problem， 或者提升佢哋 product 同埋 system 嘅 safety and reliability。咁我哋自己研發團隊咧就包括 PolyU Team 啦，咁我係其中一員啦。咁另外我哋仲有另外11個教授咧係嚟自唔同嘅部門嘅，包括咗 Electrical Engineering 啦、Electronics and Information Engineering 啦，同埋 Industrial and Systems Engineering。咁我哋就喺外國咧，我哋仲有外國嘅一啲嘅名牌大學咧，佢哋嘅 professors 同埋 scientists 咧係我哋合作伙伴嚟㗎。咁另外一個 W 就係 Where。咁究竟我哋嘅研發中心喺邊咧？就喺 Science Park。Science Park 係最後一期亦都係最新嘅 building 19W。呢個就係我哋嘅研發嘅中心嘅總部。咁除咗我哋啲研究學者喺呢度之外咧，我哋仲有 laboratory 嘅。咁我哋都有一啲非常獨特同埋先進嘅器材，主要分做3大類啦。譬如話係做一啲 data analysis equipment 啦，譬如話一啲嘅temperature and humidity 嘅 environmental testing 嘅 chambers 啦，一啲 life cycle 嘅equipment 啦。另外最獨特嘅就左手邊嘅呢個 supercomputer。因為我哋知道有咁大量嘅工業界數據，如果冇一部 supercomputer 咧，係根本係好難成事嘅。咁我哋呢個 testing laboratory 咧，亦都係科學園喺另外一座 building。咁最後一張 slide 啦嚇。咁究竟同我哋合作，或者我哋對業界有啲咩貢獻咧？咁其實無論由一個製造商，佢製造又好，佢 commission component 又好，去到 products， 去到 systems， 我哋盼望咧能夠為佢哋俾多啲嘅方案去做 maintenance 啦。咁而呢啲 maintenance 咧，再唔係以前嘅單單 corrective maintenance 啦，亦都唔係 preventive maintenance， 係 predictive maintenance。甚至我哋可以咧透過呢啲嘅研發咧，能夠令佢哋嘅產品同埋系統咧係減少佢哋嘅 failure 或者 anomaly， 從而咧提升佢哋嘅 service availability。咁最終甚至可以帶俾嗰個機構或者公司咧有 cost saving。咁我哋嘅 collaboration 主要4方面：人、機、物、法。人就係我哋一個好強大嘅研發團隊，機就係我哋有好先進嘅設備，包括咗 supercomputer。物就係指 data。透過我哋嘅合作伙伴，好多嘅大數據可以喺工業界嘅朋友嗰度嘅公司能夠俾到我哋。我哋透過啲數據咧就可以做到一啲嘅研究。法咧就係我哋用 AI technology 啦。咁我哋最終就希望打造成一個品牌，就係 Made in Hong Kong 嘅 product 同埋 system 係 number one 嘅。 咁啊，最後幾張 slide 咧都係啲圖畫啦。咁我哋嘅研發咧，頭先我講過，開始嘅時候有15個 project 啦，同我哋合作嘅伙伴咧，基本上可以分開5大個範疇。頭先我哋就由零部件去到產品去到 system， 依家我就想調翻轉，由 system 開始。system 可以講 transportation 係一個 system 啦，呢啲都係我哋合作伙伴嘅一啲嘅systems 啦。第二個範疇就係 public utilities 啦，頭先講過啦無論佢哋嘅一啲比較主要嘅一個基建啦，包括咗 transformer 啦、circuit breaker 啦等等，都係我哋一啲研發嘅關鍵性零部件嚇。咁第三就係 products 啦，有一啲 electrical 嘅 appliance 啦。今日咧我哋好多嘅 appliance 咧已經係 smart appliance， 個意思就係好多 electronics 喺度，甚至有啲 software 喺度。咁頭先講過啦，因為 electronics 同埋 mechanical parts 同埋 software 都有本身存在嘅一啲嘅 aging 同埋 latent failure 嘅。咁亦都有一啲IoT 嘅 device 都係需要做一啲研發嘅喺 reliability 同 safety 嗰度。右手邊咧就係一啲嘅 energy storage devices 啦，包括咗電池咧，陣間都有2個講者喺呢方面好詳細嘅去分享啦，亦都有啲大型嘅 power supply。第4部分咧就係一啲關鍵性嘅零部件啦。左手邊嘅就係 mechanical and electromechanical parts 啦。有中間係有一啲嘅 power devices 啦。右手邊咧係有一啲嘅 microelectronics 啦，甚至咧右下角咧有啲 sensors。今日我特別想提 sensors 咧，就係今日我哋要做智慧城市咧，好多時都利用 sensor， 甚至我哋啲 robot 全部都係 sensor 嚟嘅。咁我哋其中有1至2個 project 咧，係專門搞 integrity of sensors 嘅。最後一個咧，頭先講嗰啲全部都係硬件嚟嘅。其實軟件包括咗 data software， 佢都有自己嘅 reliability 嗰方面嘅問題嘅。咁我哋喺呢方面咧都會做大量嘅研究嘅。我今日嘅分享就停喺呢處，多謝大家。
好多謝阿容教授好詳細嘅講解。相信大家對 CAiRS 研發中心有更加嘅多嘅認識啦。如果對容教授正話所講嘅問題有咩疑問嘅話，你隨時可以熒幕上邊掃描個 QR code， 將你嘅問題打入去，咁我哋會跟住會隨機抽樣去作答嘅。好啦，到第2部分啦。容教授講完介紹完之後啦，我哋都想了解下對業界對於正話我哋嘅題目有咩見解啦。我哋今日請到金山工業集團有限公司嘅執行副總裁阿李耀祥博士，佢會帶我哋喺業界嘅角度去了解對於產品可靠同埋系統安全呢方面嘅需要同埋挑戰。有請李博士。
大家好。我喺度講少少有關工業界對產品可靠性或者安全性嘅有乜睇法？唔好意思啊，得啦。首先產品嘅可靠性對工業嚟講，對任何一個做產品嘅人嚟講咧，都係一個可以講係一個生存嘅必須要條件啦。咁今時今日喺市面上所有買嘢嘅人咧，都係即係必須要會預期個產品買翻嚟係可以用嘅。咁我諗呢個係無可避免啦。咁等下再同大家分享呢件事。首先先介紹下我哋自己公司啦。咁金山集團咧就係我哋係1965年成立嘅，喺1984年上市。咁然後咧喺1995年咧，我哋有一個即係附屬公司喺新加坡上市。到而家為止咧，我哋都係喺香港、新加坡同埋全世界唔同嘅地方做生產、分銷同埋品牌嘅生意。咁詳細嘅資料個 PowerPoint 嗰度有啦。咁我哋咧就係有2間上市公司，上面都係上市公司，下邊咧就係運作公司，有電池嘅生意、電子嘅生意、汽車電線嘅生意，同埋我哋有啲工業嘅投資。咁最下邊咧就係我哋有3個國際性嘅品牌，包括咗 GP、KEF 同埋 Celestion。 咁如果以產品可靠性，我就開始咗啦。咁我相信冇一間公司唔覺得做產品嘅可靠性或者安全性係佢嘅基本生存嘅因素嚟嘅。咁都消費者都唔會有期望話件嘢翻嚟，佢預計佢有少少問題嘅。咁所以冇問題係必然。如果對做嗰啲比較高級嗰啲產品咧，消費者會預計高級啲嘅產品咧，佢嘅可靠性會高一啲嘅，會比一啲普通嘅產品再高一啲。咁所以即係如果你話對工業界嚟講，維持產品嘅可靠性咧，係即係率直啲講係基本功嚟嘅。咁啊，一般喺呢度咧，每一間公司都會喺擺好多功夫喺，無論係由設計去到生產，去到服務，去到包裝運輸，都會擺好多功夫落去嘅。咁品質嘅嘢咧，其實就唔係靠即係品質檢驗做出嚟嘅，係一早開始由設計物料都或者生產嘅過程都已經有可靠性嘅即係元素擺咗落去。咁但係傳統搞產品可靠性咧，大部分都係基於即係實質經驗嘅累積。咁即係話以前嘅人係咁樣做就可靠啦，唔係咁做就唔得。或者啲產品去到市場見到有啲咩問題，咁然後快脆攞佢翻嚟分析改善，然後再出個好啲。咁係用咁樣嘅即係一路打一路試嘅模式去改善產品嘅。咁但係咁當然會有一定嘅問題啦。起碼第一件事就係有啲消費者會見到啲冇咁好嘅產品。咁呢樣嘢無論對公司無論對品牌都係一個負面嘅影響。咁所以如果能夠避免啲產品喺市場上需要一個學習期，或者能夠預先預計到啲產品嘅可靠性係點，由一早已經做咗應該做嘅嘢咧，其實對工業嚟講係非常重要，同埋嗰個貢獻係好大嘅，都可以講話係一個突破性嘅做法嚟嘅。咁想要做到呢啲即係領導全球或者領導行業嘅產品品質咧，其實要嘅功夫都即係非常之多。咁每一個環節都要照顧到嘅。咁無論喺對新產品或者已經做緊嘅產品，喺做可靠性嗰度咧，係要長期時時都關注。咁如果啲產品係做出嚟比其他人都特別可靠嘅咧，我相信喺市場上咧會係一個好大嘅競爭優勢。咁但係如果啲嘢係唔可靠咧，亦都可能係導致到即係喪失市場嘅一個重要原因嚟。咁我哋自己公司嘅做電池嘅生意咧，亦都喺同CAiRS 有一啲合作，而主要咧就係即係去建立利用 CAiRS 嘅技術，去建立一啲通過 AI 同埋大數據去建立一啲能夠預計產品可靠性嘅方法。等我哋可以喺新產品出嚟之前咧，就已經能夠盡量將產品嘅品質做到最好。咁呢樣嘢咧都係，正如我正係講係幾新嘅。咁亦都我哋相信，達到呢個目的咧，會對我哋公司嘅產品咧係有一個好大嘅正面幫助。咁講我哋電池咧，電池其實係一個即係喺中國咧都係一個最大嘅電池生產商。咁我哋做一次性嘅電池啦、充電池啦，同埋同充電池有關嘅產品供應，除咗消費者之外咧，消費者我哋通過 GP 嘅品牌啦，咁亦都供應好多工廠啊或者其他電池嘅品牌嚟提供俾佢哋咧，我哋嗰啲即係產品嘅。咁我想分享嘅大致係咁樣。咁啊，唔該晒。
好，唔該晒。好，唔該晒李博士精彩嘅分享。 咁同樣地啊，如果有問題關於李博士正話所講嘅內容，你哋都可以將畫面上面嘅 QR code掃描啦，然後輸入你哋嘅問題，我哋等一陣 Q&A 嘅 session 會隨機抽出問題去作出解答嘅。好，聽完李博士嘅分享之後，我哋會下一位我哋嘅學者啊，同我哋分享啦。Our next speaker is Dr. Stephen Bowles, Associate Professor at the Hong Kong Polytechnic University. The topic of his presentation is Reliability and Safety Research Methodology with Industrial Applications. Dr. Bowles, please.
So I'd like to thank the organizers for this opportunity to talk to you today, and I'd like to thank everyone tuning in at your office or at home, wherever you may be on this lovely afternoon. So this talk is going to cover kind of a broad range of subject matter and technical level. So we'll start out kind of slow before we get a little bit deeper. And so first things first, let's talk about energy. So I think we all know that some people call it an energy crisis, but others of us might call it an energy opportunity. All right. And so if we look at, for example, just taking oil as a proxy and how much oil has been consumed over the past 30 years by different geolocations, we see that places like Asia are still increasing to use energy. North America and Europe, these are more developed markets. They're also using more and more energy, even though they are pushing for better energy efficiency. They're still using more energy. And places like South America, Central America, Africa, Central Europe, I mean, these places are still yet to really blossom and bloom in terms of their economies and growth. So we anticipate that some of those places like Africa, as soon as they really start turning on their economies, they're going to boom in terms of their demand for energy. So that does present some challenges for the future. So when we think of energy, most of us will equate energy with electricity, and that's fine. That makes for a good talking point here. So if we consider what does the electricity mix look like in terms of power generation, there's a few different technologies that are used to make power. We have coal, which has historically been very important, and you see that still makes up a very large share of our power generation globally. Oil was another big factor, although it's decreasing lately. And then we have other technologies like hydro and nuclear and natural gas that are important. And just in the last, let's say, 10 or 15 years, we really see this growth in renewables. And so this is solar technology. This is things that wind power, another one. People are starting to get very excited about. These are going to be greener opportunities. Hopefully don't have such bad pollution. But in terms of power and energy, there is a connection that we need to make here and a reminder. And that is that the connection between power and energy is linked by this unit of time. Okay, and so energy divided by time will give you the power. So this is very important if we want to consider renewable energy, because there is a time component. And we all know that the sun is shining on beautiful days like today, but when the sun goes down, you need to have a way to store the energy that you've created during the daytime so that you can use it at night at home to play on Zoom, to talk to your friends, to play PS5, what have you. Okay, so there is this time component that is not trivial, and it needs to be solved. So we need this energy storage component to account for time. So how do we do that? Well, right now, what the world is pursuing is by ramping up things like natural gas. And that's why on the last slide, if you look closely enough, you'd see that actually natural gas consumption is growing. And even here in Hong Kong, that's true. We know that there are some power plants in Hong Kong that are upgrading so that they can use natural gas. And that's because natural gas power plants can turn on very quickly. They can quickly meet the demand for electricity as consumers need it. However, that lag between time is important, because if you generate power and you don't use it, it gets wasted. Okay, so having an energy storage solution is really absolutely necessary if we're going to have solar energy and wind turbines to facilitate a green revolution and really make our lives and skies much clearer and healthier in the future. So then the question is, how do we store this energy? What different technology options do we have? A couple of these technology options are what I would call old school, or they've been around for a long time. So you have options like pumped hydroelectric power. And so that's where you're essentially just taking water from a lake or an ocean or river, and you pump it up a hill. And you're storing it somewhere in higher elevation until the time that you need it. And then you're going to release that water flow down the hill, harness the power of gravity to turn that stored energy into the power you need at that moment. There are other ways that are popular, been around for a while, things like a flywheel. And that is essentially just a heavyweight object that is rotating very fast. And so you can spin a wheel as fast as you possibly can. And if you have low friction and that wheel can spin for a long time, then you've essentially just stored energy until the time that you need to harness it, where you then hook in a load and you can tap some of that energy as the wheel speed slows down. People are thinking about ways to thermally store energy. So actually you can, for example, take water and you could freeze it and you could make ice. And then you can let the ice thaw and you can recover some of that energy. So these are all ways to do it, ways to store energy. But there's serious problems with all of them in terms of how well they can scale to meet the demands of society in the future. And this is where electrochemical technologies have a very, very big advantage, because those examples that I gave on the previous slide, things like hydroelectric power, these are nice, but they do take a lot of resources to make happen. And then worst of all, they're not very efficient, because you have to consider how you're going to convert that energy. So for example, if you're going to use solar power and pumped hydro together, you're going to essentially create electricity, and then you're going to need to convert it to mechanical energy, and you're going to push that water up a hill, and then you're going to store it, its potential energy, you're going to release it, and you're going to convert back from mechanical to electrical. So this only really works well if you have a very large scale system and you highly and precisely tune it. There's very little flexibility with these kind of large scale mechanical based systems. And so this is where something like an electrochemical storage device would have an advantage. And so in principle, the electrons that you generate using your power source can be the same electrons that are used to store chemical energy. And then when you want to tap that energy, you can recover those same electrons. You don't have to convert them using any other way. So what kind of electrochemical device are we talking about? There are some capacitors, but most people will think of batteries. Okay, and so batteries have this intrinsic advantage of being more efficient because you don't have to convert energy to thermal energy or mechanical energy in order to harvest it at a later time. Of course, this is all in principle, okay? So ideally, batteries have very little loss associated with their energy storage capabilities. But we all know that the real world is not the same as our textbooks. I think our students at PolyU experience that the hard way when they graduate, right? Okay, so what options do we have for batteries? I think everyone knows about lithium-ion technology, and this is just a bit of a reminder about lithium-ion technology. So if you look at a periodic table of the elements, and these are all the elements that we have accessible to us, you may remember from your introductory chemistry class. If we see the position of lithium up in the second row there, we see that it's actually one of the absolute lightest elements on the periodic table. And so as we go down the periodic table, elements get heavier. And this is the reason why people are so excited about lithium, is because there aren't many options for materials and elements that are lighter than lithium. So if you want to store energy and you want to store it in a as lightweight kind of package as possible, because you have some mobility or portability applications in mind, really your only option is lithium. Other people have tried lead in the past, lead acid batteries, very good technology, been around for 100 years. Unfortunately, lead is just too heavy to be used for these mobility applications that we're excited about. I will mention hydrogen is one row above lithium. Hydrogen is very exciting. Actually, I just participated in a conference earlier this week on hydrogen economy 2.0. So that is something that is very active in Hong Kong. It's very exciting to see that. Hydrogen also has a lot of things going for it. Of course, there's problems associated with that, but nevertheless, very interesting. However, today's reality centers around lithium as being our primary battery technology for energy storage. Of course, if we're going to store a lot of energy in a small package, that's going to have some risk. And the more energy we store, the higher risk associated with the battery. And this is very fundamentally linked. We can't really separate these two things. If you want your car to drive for 500 kilometers before you need to recharge, you have no choice but to have a lot of energy stored. And that inherently will create a lot of risk. Similarly, if you want your phone to last for 3 days between charges, you're going to have a lot of energy in your pocket. Okay, so these things we just can't get around. So most of the world knows this, and we're seeing, if we look at the trends for lithium batteries based on applications, whether it's consumer electronics, whether it's stationary storage, whether it's electric vehicles, everybody is pursuing lithium batteries. And I think we've seen for a very good reason, right? Because you can store so much energy in such a small package. But this is going to create, and this plot is interesting because they even account for COVID-19, the pandemic. Some things did slow down, right? We know that economies are suffering around the world. That's true. But the demand for energy storage devices like lithium batteries is not slowing down. That's still increasing, moving forward. All the things that lithium technology has going for it are in demand by these different applications. So we're going to continue to see this trend for the next 10 or 20 years until there's other competition out there. But as we saw from the periodic table, we're really limited in terms of what can ever compete with lithium-ion batteries. Now, just a little reminder for you, how does a battery work? We essentially have three important components. We have a positive electrode, a negative electrode, and an electrolyte. And so during the discharge process, we have lithium ions that are traveling through the electrolytes. They're going to the positive electrode. At the same time, electrons are going through an external circuit. They're doing some work. Maybe they're creating some light, and they're going to meet up at the positive electrode to complete the circuit. And that's what gives us light or energy when we want it. Conversely, if we apply a voltage or a potential across those two electrodes, we can then reverse the direction, and the lithium ions should come out of the positive electrode. They should go to the negative electrode, and electrons will go again through the external circuit. So just a reminder for you for what a battery looks like on the inside and the principle of operation associated with it. Now, we're here at the Center for Advances in Reliability and Safety. And of course, we've just talked about how much energy is being stored in a lithium battery. So we see that this is very important. So let's just refresh ourselves with some contemporary examples of safety and reliability as it relates to lithium batteries. The 787 Dreamliner, beautiful plane, uses composite materials for the fuselage instead of aluminum. Very revolutionary in terms of the technology. They also tried to put some lithium battery packs inside for their control systems and flight systems. That didn't work out so well. So I think we remember that these planes were grounded for some period of time so they could fix the problems that were going on. They don't want to have batteries catching on fire while the plane is 30,000 feet up in the sky. So they need to do something and find a solution. But actually, I chose this example for a different reason. And that's because of the regulations that are associated with it. So now you know that during normal times, when you would go take a flight, you're always asked, what kind of battery packs do you have in your checked luggage? You can never put a spare lithium battery into your checked bag. Every time you try to fly, you're going to get asked about this. It's going to be a question that's raised. And this just goes to show you that even though the safety problem is solved for the plane, the regulation problem is not entirely solved. And so the regulation will last in perpetuity. And so when we think about reliability and safety, of course, we want to get things right for our own personal safety, but we have to remember the downstream effects of this, and that it will affect future generations of people, our kids and grandkids. Most likely when they go fly on a plane, they're not going to be able to put spare lithium batteries in their checked baggage, even if the reliability is perfectly improved in 50 years' time. So these regulations can carry forward from an institutional or bureaucratic process. Another example, a Tesla. So we see Teslas in Hong Kong. It seems like I see them every 2 minutes when I'm walking on the street or less. So a very popular car. They've done a very good job of branding themselves as the leader in electric vehicles. And if we look inside, what is the core technology of a vehicle like this? It really comes down to the 7,000 lithium-ion batteries that are stacked inside the battery pack. And so this battery pack may cost $20,000 US, $30,000 US. It stores about 100 kilowatts of energy for, I think, the top of the line model. That's equivalent to about 85 Hong Kong dollars worth of electricity being stored in one of these battery packs on a full charge. It's very important. I think we know that the reliability and safety of a vehicle when you're driving on the freeway or the highway at 100 kilometers an hour, you really don't want anything going wrong with that. Furthermore, we need to consider the safety and reliability life cycle. So the reason I gave this example is because we need to consider what happens when you decide to buy a new car. And if you want to get rid of your old Tesla or your old electric vehicle, because I think there's a lot of competition coming for Tesla, what are you going to do with that car? You're going to give it back to a dealer, you're going to sell it. Maybe somebody wants to buy a used one. But even if the battery pack is degraded, it doesn't mean that you can just throw it in the trash, right? The safety and reliability of a used lithium battery is still a very important issue. That's one I think people, very smart people in Hong Kong are trying to solve that right now. So it's something we have to think about as society. What do we do with these used batteries? Because they need to be treated safely and reliably in the future in order to have a green environment. We can't just dump them where we see fit. Okay, and then lastly, everyone, I think, in this room and even our kids at school, they all have these mobile devices in their hands nowadays. And so keeping in touch with people is important. If you want to have a battery that lasts for some time in your mobile device, you need to have reliability in that. You should not be relying on software tricks in order to try to make your battery seem like it's lasting a long time. So we see many industries and many downstream effects for reliability and safety of lithium batteries. And so this is something that we want to approach at CAiRS. So we have some strategies for research, but of course we need to think about how are these batteries degrading to begin with. So then we can look at the inside. And as Professor Jung mentioned, we want to look at the physics of failure, right? So we want to look at what are the mechanisms involved with a battery failing. And so one example that's quite well known is lithium plating. And so this arises because the difference in the chemical potential between lithium and the surface of the anode may get very small. And if it gets too small, then you may have some cases where you're going to have lithium plating onto lithium itself. And so this can be observed in real time using an experimental approach where you can watch lithium growing. Now, if that lithium grows too much and it goes from your anode side to your cathode side, you're going to have a short circuit and you're going to have failure. How else can a lithium ion battery fail? You can have overcharging. So here we see this schematic that looks at capacity versus voltage. And we see a lot of different chemical equations here on this plot. But what's important to point out is that in the case of overcharging, you can have cathode decomposition leading to gas generation, or you can have, if you discharge too much, you can have electrolyte decomposition that leads to gas generation. So if you charge too much or discharge too much, those are both major risk factors for your battery. You can generate gas inside the package itself. If you generate too much gas, you may be prone to explosion or to some kind of failure. So I think state-of-the-art batteries try to account for that now. They have vent tabs right on them. So if you generate too much gas, there's a way to get that out, but it's a very serious problem. So not only for the cell itself, but the electronics that accompany the batteries. So the battery management systems or the circuits that are involved, it's also important that those are operating reliably and safely in order to have the cell quality and cell integrity maintained during operation. And then lastly, I'll just mention some manufacturing issues. So I think there was a Samsung battery that suffered this fate in one of their previous models a few years ago. And this is just a case where you think that you are building your battery in the right way, but if something is misaligned inside your factory or inside the process, and you are welding two things incorrectly, that can lead to catastrophic events later on once your product leaves the factories out in the consumer market. So these are all things we have to consider when we think about the physics of failure. Now, all of these for a lithium battery, all these examples are important because the things inside the battery are all quite flammable. And so if we have any of these cases that lead to thermal runaway, where the cell itself is getting too hot, you may have, for example, the electrolyte start to combust, catch fire. The lithium, if that gets exposed to air, that can also catch fire. The cathode materials are oxidizable depending on their state. And so it's been shown that during thermal runaway, the battery temperatures can get up to 900 C. 900 C is incredibly hot. You do not want a 900 C battery in your pocket. That's going to hurt you pretty bad. So we have to keep these kind of things in mind when we think about the safety and reliability of the next generation of lithium batteries. So how are we going to do this? One of the best approaches is sensing. And so sensing in batteries has been around for a long time. So people have been pursuing these routes for over 100 years, trying to figure out how to best characterize the state of health and the state of charge of their cells. So there's many different approaches, whether that's using something like an ammeter or a potentiometer, employing thermocouples, impedance, spectroscopy, many different approaches. But we'll mention that in the last maybe 5 to 10 years, the excitement about a technology related to fiber Bragg ratings is looking very promising in batteries, and that's for good reason. So here at CAiRS, our approach is to deploy a so-called canary device. Okay, and if you think about where this term canary comes from, that was a little bird that was brought down into the coal mines a long time ago. And if there was any problem with the air quality, either from a toxic gas being released or from a lack of oxygen, those kind of things would instantly influence the canary's state of health. And if the state of health of the canary failed, people would know that it is time to go. Okay, so what we want to do at CAiRS is to use this same kind of approach for a lithium-ion battery, deploy a canary device in a cell to try to get better information about that state of health. So we're pursuing, as I mentioned, this fiber Bragg rating, and this is essentially where we have a mirror that is embedded in an optical fiber. And what we do is we send a pulse of light down the optical fiber, and we look at that reflection that is generated on that light by the mirror. And so if we track the reflection that is inside the optical fiber, that tells us a lot about what's going on. Because if the fiber, the optical fiber, which is maybe, let's say, 160 microns or 120 microns in diameter, if that is being subjected to temperature changes or to mechanical changes like pressure or strain, that will tell us instantly because there is going to be some physical change in the fiber Bragg grating itself that changes how the light is being reflected, and it will tell you instantly what the temperature is or if there is a mechanical condition that is important. Also quite relevant is that this device does not have any electromagnetic interference. So it can operate inside something like a lithium-ion battery, even though there are live potentials around, there are 4 volts, 5 volts perhaps, but it's not going to influence the reflected peak signal that is generated in the device. Okay, and this also has a very small form factor. I mentioned the 120 microns, so then it can slip into some other larger system, and in particular, perhaps a lithium-ion battery. So with these sensors, we can do some exciting things. For example, we can use the temperature change and the pressure change to investigate what happens as a battery is being cycled. So for example, on the very first charge of a battery, you may have some gas generation that occurs naturally, and that will give rise to an increase in pressure inside the cell. And these devices are very well suited to observe that pressure rise. And at the same time, they can also track the thermal changes. So when the chemical reaction is happening inside the cell, these sensors will tell us by how much the temperature was changed inside that cell. And so we can use this approach by having pressure monitoring and temperature monitoring inside the cell to gain more insights into both what is happening with the chemistry and also design concepts and eventually reliability and safety. If we want to put together multiple sensors, and so for example, we may put one sensor inside the cell, but then we can put another one on the surface of the cell and perhaps even another one somewhere else. If we have information about this delta T or temperature gradient, that tells us more than just what temperature things are at. That actually starts to give us some information about heat and heat transfer and the origins of heat. And so if you think about, what you care about, you don't care that your phone is hot. You care if it's generating heat. Okay, and those are two very different things. And if your phone is generating heat, then it's a serious problem. And for example, for the battery, we want to know why that is happening. What is the origin of that? So we've been able to look into this to some extent, and we can see things like even the chemistry of the active material in the battery is very important. And the way that lithium or sodium for a sodium ion battery goes into the active material will determine how much heat is being released, and we can quantify that using this multi-sensor approach. This approach also gives us some insights into cell design, how much heat is going to be transferred based on certain charging conditions. So it gives us a good idea about thermal management strategies as well. I mentioned that electric vehicle battery pack with 7,000 cells. It's very important to think about thermal management, because if all of those are generating heat at the same time, you need to have a very clear cooling strategy. And so a device like this gives unparalleled insights into what you should think about when you're designing a large battery pack or collection of cells. It can even do things like validating the role of additives. So I mentioned that inside the electrolyte is where lithium ions go back and forth between the positive and negative electrodes. And so that electrolyte is a liquid, but it's this kind of a special liquid in that everybody has their own special formulation consisting of little bits of different chemistries that are designed to do different things. But what this sensor approach allows us to do is actually quantify the role of each of those so that we can pinpoint how much gas is being generated based on certain additives. Can we, for example, reduce the amount of gas that's generated so that there's no intrinsic pressure buildup during the first charge, so we can make sure that there's no risk of explosion or having to use that vent feature that's built in to the state-of-the-art batteries. So what does this look like in the future? In the future, we see this improved safety, reliability, and health. And just in the same way that people have been using this approach for the human body, if you go in for surgery or a checkup, you may have a probe that's now inserted inside you to look around and wants to see what's going on. And that helps you diagnose your own health. In the same way, we want to take the same approach for an energy storage device like a battery. Insert an optical fiber. We get some reading about what the state of health is. And then ideally, all these things can start talking to each other, right? So we know about IoT on the horizon, the Internet of Things. Devices with 5G are going to communicate with each other. Can our sensors then be linked to a larger system, more advanced battery management systems, downstream effects where we see these benefits pay off? So thank you for your attention. I'd like to mention that there's a lot of exciting things we can do. This example is just about batteries, but the same approach can apply to things like fuel cells or catalysis or other things in the energy space. So there's a lot of opportunity there if that is your industry or your business. We also have opportunities within our own staff. So I think you can go on to indeed.com.hk, something like that, and you can find us. There's some opportunities available if this is something you want to be part of. So thank everyone.
Thank you, Dr. Bose, for your professional presentations. So again, if you have any question to ask Dr. Bose, please scan the QR code on the screen and enter your questions. 好啦，好快就嚟到我哋嘅 Q&A 嘅答問環節啦。咁我哋會隨機抽出幾條問題啦，咁再隨機抽出幾條問題，再問問我哋嘅嘉賓嘅。咁我而家睇睇我哋收到有啲咩問題先啦。好。其實都好多問題想問嘅，不過時間問題啦，我哋可能淨係可以抽幾條問題嘅啫。咁第一條問題，或者我哋先問一問Dr. Lee 先啦。咁有啲聽眾想問喎，佢話從業界嘅角度，產品可靠同埋系統安全係固然好重要啦，但係佢都想問問Dr. Lee，控制成本嗰方面，你覺得 CAiRS 有乜嘢可以扮演到咩角色？佢想問問你。
或者呢個問題咧係比較即係要考慮多角度。傳統講產品生產講生產成本咧，就好多時即係講話出廠價。咁但係出廠價咧，除咗物料啊、人工之外咧，仲有嗰個生產嘅效率。譬如有幾多產品喺生產嘅時候，因為物料或者工序嘅可靠性問題而導致到佢生產效率降低咧，生產效率降低咧就會直接影響到生產成本啦。咁呢個最近身嘅。咁但係實際上產品做完出嚟之後咧，直至到去到消費者最後買嗰個用家嘅手上，同埋佢用咧，仲有好多成本，包括咗運輸啦，包括咗喺市場上有幾多服務。即係如果個產品好快就壞啦，要攞翻去整，咁你有服務中心嘅成本。如果亦都有個維修嘅成本，如果唔好彩嗰件嘢壞到即係需要好大量嘅維修咧，可能要換嗰個新嘅俾佢，咁嗰啲都係成本。咁我相信，如果 CAiRS 能夠喺產品嘅可靠性方面可以做到一啲即係改善嘅工程，無論喺生產上、設計上、工序上，甚至嗰個產品嘅可靠性都可以提供到改善嘅方案咧，我相信對一個做產品嘅人嚟講咧，可以生產到可以減省到成本咧，應該係即係毫無疑問嘅。咁當然我哋有傳統嘅方法去做，但係亦都即係憑經驗、憑市場嘅業績嚟揾到改善嘅方案。但係如果能夠喺未做嘅時候，通過無論係 AI 大數據或者嗰個即係預期性 predictive 嗰個 model 可以作出一啲改善咧，我相信對廠家嘅貢獻咧都係會好大嘅。
好，唔該晒，多謝李博士。咁好啦，我哋再睇睇有啲咩問題啊。好，咁第二條問題或者問一問容教授啦。咁有人問CAiRS 其實可唔可以喺幫助到業界減省到成本喎？容教授。
未答呢條問題之前咧，我想回應翻李博士頭先嗰個答覆啦，個答案啦。絕對可以嘅，即係 CAiRS 咧，絕對係有信心，亦都有咁嘅能力咧，去幫咗業界咧，係喺 cost 呢方面能夠係去減省嘅。咁好最簡單，頭先李博士提到咧，即係喺品質或者可靠性方面咧。無論係我哋叫做4M 啦，係咪？好多時候我哋嘅 quality 同埋 reliability 嘅問題都係嚟自4M。M 就 method 啦、material 啦、manufacturing process 啦、man 啦man 即係作啲人啦咁人嗰方面我先唔講先啦。material、methods 或者嗰個即係或者 machinery 即係呢啲咧，其實咧，我哋都可以用所謂嘅 physics of failure 咧，去睇睇究竟乜嘢原因去造成我哋嘅產品無論係售後有 anomaly， 我先唔好講 failure， 或者係一啲唔尋常嘅情況發生，我哋叫 anomaly。呢啲 anomalies 話好 failure 好，其實喺出廠之前可能已經係 build in 咗。咁呢 build in 嘅成因咧，我哋可以用 physics of failure 咧。去睇一睇，咁所以咧，呢一方面嘅研究咧，我哋會係相當多嘅咁所以回應翻頭先李博士嗰個問題咧，絕對係喺呢方面咧可以幫到手嘅。咁回應翻頭先Samuel 你提嗰個問題咧， 我覺得作為一個產品或者 system， 用翻頭先李博士所講，售後即係賣咗出街啦，去到個 user 嗰度啦。若果佢個可靠性提高嘅話，或者係 safety level 提高嘅話，起碼有3個唔同層次同 cost 有關係嘅 saving。第一，我哋知道產品若果售後，如果唔好講話 failure 要 replacement 啦嚇，甚至佢嚟去 repair， 其實係一個錢嚟嘅，係咪？如果 reliability 嘅 level 提高，佢售後個服務係唔需要常常有 repair 嘅，或者係一啲嘅anomalies 出現嘅，咁其實對嗰個公司咧嗰個成本係減低。咁如果你真係再做埋 replacement， 咁更加嘥錢添啦嚇。如果你 reliability level 提高，你根本就唔會有 product replacement 啦，甚至有一啲極端嘅情況咧，你有 product recall 嚇，即係如果 reliability 唔好嘅話，你 product recall 仲大件事，係咪？咁所以呢個係直接同成本掛鈎。第二個同成本掛鈎嘅咧，就係個 branding。若果我哋嗰個 reliability 產品，舉例如電池又好啦，或者係一啲嘅 BMS 嘅 battery management system 又好啦，大型嘅 power supply 又好啦，如果我哋個 branding 係 reliability 嘅 branding 做得好嘅，肯定咧我哋嘅銷量一定係高嘅啊！咁仲唔計嗰啲 quality image 嗰啲 intangible 嘅 benefit 係咪？咁呢個係第二個同 cost 有關係嘅。再深一個層次就係 maintenance。我哋知道咧，有一啲嘅大型嘅公司咧，佢其實用電池用好多嘅。舉一個例，上個星期三，我同我個團隊研究團隊咧，去同一間 local 嘅一間好大型嘅即係巴士公司唔好講邊間啦，我哋傾一啲合作計劃。講到差唔多最後咧，佢就問咗個問題：喂，容教授，你哋搞唔搞 battery 㗎？我梗係搞啦，我哋其中一個就係搞 battery 啊嘛。佢話我哋依家巴士啊，即係通常咧幾時會換電池咧？2年 ，OK， 好啦，就當清一色係2年。咁咧，你喺歐盟5型嘅巴士又係2年換電池，歐盟4型又係，歐盟6型都係，其實唔一定嘅，因為個 battery 喺唔同嘅 user condition， 喺唔同嘅 environmental condition 咧，其實佢嘅 life 係唔同噶嘛。如果透過我哋 CAiRS 嘅研究咧，我哋可以話到俾大家聽，歐盟6型嘅電池唔使換咁密嘅，歐盟5型嘅係換電池嘅時間性要幾多嘅？其實唔係得一刀切㗎。嗱，依家今日好多做 maintenance 梗係一刀切嘅。嘅意思即係話，我有個產品下底有好多唔同嘅零部件，或者我有 system 下底有好多唔同嘅關鍵性零部件。咁我哋一次過大家都年半做一個 overhaul， 或者做一個 maintenance， 或者3個月或者6個月。其實每一個關鍵性零部件佢遇到嘅 environmental condition 同埋 user condition 都唔同。我哋作為 CAiRS 咧，我哋就話到俾廠家聽，其實咧可以有不同嘅 maintenance strategy。喺呢方面其實就慳到錢咯。再者，我間巴士公司講話2年啫，其實有啲啊1年08個月已經死咗啦，嗰個電池咁啊慘啦，嗰個巴士咧就喺路中間跪低咗。咁跪低咗帶出嚟咩啊？就係 cost 咯，唔好講形象先啊！你又啲乘客啊換巴士啊諸如此類，所以咧長話短說咧，上次同嗰間巴士公司傾完咧，我哋話另外一個同佢可以合作嘅咧就係搞佢嘅 battery， 就係透過我哋嘅大數據分析，透過我哋嘅 POF 頭先啊 Dr. Bose 講嘅 physics of failure， 我哋都話俾巴士公司聽乜嘢類型嘅電池乜嘢嘅品牌用喺乜嘢嘅巴士上高，有乜嘢嘅 maintenance strategy。嗱，咁呢個咪直接同 cost 有關係咯，係嘛？或者咧，我哋都將時間俾翻你問另一條問題啦。
好多謝阿容教授。咁我哋再睇下有啲咩問題啦。Okay, there's one question for Dr. Bose. Okay, one of the question is they want to know: is it possible to build in the FPG sensor into the battery in order to keep monitoring the battery status in daily use? Dr. Bose?
Yeah, so if we want to use this FPG technology for daily use, that presents a different proposition because then we have to consider the cost. And I think Dr. Lee can tell you that if you want to live in the real world, then you have to think about the cost. And so having the back-end support that enables FBGs, if you want to put that in your phone or in your automotive battery, you have to be very strategic about how much you want to spend and how much you want to dedicate in terms of volume and weight to the back-end equipment that enables the FBGs to operate and to give you that additional insight into what is happening inside your cell. So although it is technically possible, it may not always be the right choice.
Okay, thank you, Dr. Bose. OK， 咁我哋都仲有好，我再睇一睇，就冇再有，仲有冇時間？我哋再答多個問題。好啊，好啊。咁我哋容教授啊，我哋再問多個問題啊。都有個觀眾都想問佢話 CAiRS 點樣可以做到將啲研究落地喎？容教授，
呢個問題非常好啊！先講一個背景啦。我相信呢個聽眾問呢個問題咧，就可能成日有一個感覺咧，啲教授啊研究咧，通常都係閂埋房門出下 paper 就算數嘅。咁咧，我哋呢個團隊咧，我講 CAiRS 嘅團隊就唔係嘅啊！我哋盼望我哋所有研究，當然我哋會做一啲基礎性嘅研究啊。其實頭先啊 Dr. Bose。What he present is a lot of fundamental research there。但係 at the end of the day 咧，我哋希望呢啲研究 fundamental research 咧係可以有應用嘅一個 scenario。所以就係因為咁樣咧，我哋雖然呢個研發中心咧成立咗只係好短嘅時間，但係業界俾我哋嘅聲音同埋支持係好大嘅，正面嘅聲音當然。所以見到我哋即係合作嘅伙伴咧有成10幾20間嘅，咁。點解佢哋會嚟同我哋合作咧？就係盼望我哋研究能夠落地嘛。嗱，所以亦都喺我哋嘅研究裏邊咧，我哋其實有一啲嘅 products， 有一啲嘅 system 咧係 in mind。咁頭先我哋有一張 PowerPoint slide 咧，亦都俾大家睇到咧。有唔同嘅 themes 係咪？關鍵性零部件啦，甚至關鍵性零部件都好多唔同類型噶嘛。有 products 啦 ，product 好多唔同類型噶嘛。再加上嘅基建啦，即係 public utilities 啦、transportation 啦、software 啦。咁我盼望咧，藉着咁樣嘅一個叫 showcases， 我哋話到俾人聽 ，CAiRS 嘅研究咧，唔單止落地，並且放之四海皆準，因為 reliability 同埋 safety 係個個行業。個個製造商都需要嘅，咁所以透過依家咁多業界嘅正面嘅回應咧，可以話到俾聽眾聽，我哋未來呢幾年，我哋嘅研究咧將會唔單落地，係貼地嘅。
好，多謝容教授。咁今日都好多謝咁多位嘉賓啦、嚟臨啦。Thank you for all the guest speakers together to our webinar。好，咁今日嘅研討會都去到尾聲啦。咁我哋而家有請主辦機構 CAiRS 研發中心嘅總監及執行董事容教授為我哋致閉幕詞嘅，有請容教授。
So thank you first of all for all the audience. No matter you are at home or you are, because a lot of people working from home. No matter whether you are from home or from your office, you are attending this webinars. So thank you for your time. And of course, I'd like to say big thank you to the two doctors on my right-hand side, Dr. Brian Lee and Dr. Steve Bose. And we hope that everyone would enjoy the webinar today in this afternoon. And we also hope that the content of the webinar will be useful to you now or in the future. And as a final remark, there will be upcoming a few webinars. Hopefully that will be free or even more. And 2 regional and international conferences will be organized by CAiRS. And because of those events, we'll be inviting more industrial speakers and professors from overseas universities. They will be presenting their fundamental research and applied research and the applications from the industry on safety and reliability. If you need more information, you're welcome to log into our website, www.CAiRS.HK. And you have a lot of information more than what we talk about this afternoon there. So we hope to see you very soon, and stay healthy and stay safe. Thank you.
好多謝阿容教授，多謝各位。CAiRS 主辦嘅網上研討會已經圓滿結束，希望大家可以把握產品可靠同埋系統安全所帶嚟嘅挑戰同埋機遇，繼續發展你嘅事業。多謝各位，多謝各位嘉賓。Thank you very much.